So I'm going to dig deeper into this equation right now, and I'm going to look at, first of all, partial sigma x partial x. So partial sigma x partial x can be redefined as partial x of sigma x, and we just went through the step of saying that sigma x is my over I. So it's partial x of my over I. Now, I can certainly vary over x if you had a non-prismatic beam, and we had one already for homework. But for this example, I'm going to just pull I out. It does not vary with x. So I have minus y over I times partial x mz. And the next question is something that everybody in the room should be able to answer. So hit the pause button if you can't answer this question immediately. What is partial x mz? So go ahead and hit the pause button. The answer, of course, is minus shear. So be careful with that sign. I made a note here. See Appendix D1 for the sign if you're a little bit behind on that. So partial sigma x partial x is minus y over I times negative shear. And we have this expression in here, Vy over I. And we're going to put this back into this equation now, which is the sum of the forces in the x equilibrium equation. So I have that integral. Remember, the lower limit is y1, the upper limit is y max, and I have Vy over I dA, which was this expression in here, minus tau xy times b. Now I'm going to look at this integral slightly more carefully, and this is a very thought-provoking part of the derivation, if you want to call it a derivation. We're just exploring fundamental ideas here. Does v vary between the limits of the integral? And does I vary between the limits of the integral? And the answer is no. V and I can only be functions of x. Now certainly v can vary as a function of x, and that's the starting point of this whole thing, that the shear does vary as a function of x. And we already said I doesn't vary in here. So v and I are pulled out, the b of course is pulled out, and we have the integral of y dA. And that you may remember from even from calculus way back when, that's known as the first moment of area. So you have an area times an arm times a moment arm. So that's why they call it the moment of area. And we call it capital Q. And Q is always a source of anxiety for some undergraduates in the sophomore level mechanics class. It's the area above or below the axis of investigation multiplied by the distance of that area centroid to the neutral axis. And I actually make them memorize that in a sophomore class. So there's a couple things that I want you to notice about this equation in here. That it meant, first of all, completely isolating that green element, pulling that little green element out. Q over B is an interesting idea here, that tau can be maximized if Q over B is maximized. Not necessarily Q, but Q over B. So if you have a funky cross-section, you need to maximize where that ratio is. And we're always defaulting to the neutral axis as maximizing that. But I'd like you to just think about this idea of a very, very odd shape. Is Q over B actually the max at the neutral axis? And you could analyze either area, take the easier one, and notice one more time, this is always in plane maximum is the undergraduate version. Even in your sophomore level books, you'll see when you're doing your Mohr circle problems, tau in plane maximized versus tau max. That one is out of plane typically. Okay, so here's your homework problem. I will begin it for you. It's a cantilever beam with a point load coming down. Y is going down, X is going to the right here. The height is 2h. Well, let's call it 2c to keep everything consistent. And the question is to find u as a function of x and y and v as a function of x and y, but include the shear deformation. And we're going to start with those big boxed equations, those equilibrium equations, so go find those.